All right. All right. We are doing that. Okay, let's get started. It's just time once again. Ready? We're all ready? Okay. Homework 6 this Friday. Lab 7. I'm going to go spend almost all of lecture going over Lab 7. You will need a kit of parts that will be issued to you tomorrow in section. The Bell staff will come up to B104 at the beginning of each section, but they will only stay for the first 10 or 15 minutes or until everybody's gotten who's there has gotten their parts. Let me turn that on. You can come earlier to an earlier section if you want to pick up your parts. Yes?
Would you be able to go down to Bell's if you showed up in between?
Yes, you'll have to go down there and get it yourself if you're not outside the first 10 minutes of a section. Okay? Okay, and you're going to need your parts to do the labs. Okay, all right, so any questions before we start going over Lab 7? Okay, let's do it then. All right, so Lab 7, you're going to be building 2 circuits. The first is a ring oscillator, and the second is a D flip-flop. To build these circuits, you are going to be using wires and discrete parts that have logic gates on them. And in order to connect them, you're going to be using a breadboard. Okay, this is a breadboard. It's got holes that you can plug wires into, and it's very important to understand which holes are connected to which holes. Okay, so there are 4 sections. In the 2 outside sections, all the holes within a column are connected. So this is a good way to distribute power and ground. So if we connect this column to power, then any wire you plug into this column is grounded. Same thing for your +5. Okay. In the 2 center sections, the opposite is true. The holes within each row are connected. So these 5 holes, if you plug any 2 wires in there, they will be connected. And over here, these 5. Okay, there's no connection across the center divide. This is the continental divide, so to speak. All right. When you wire up your board, you may be in a hurry, and haste makes tremendous waste. When you are building your circuit, you do not want to end up with something like this, because invariably it will not work, and then you'll have a headache figuring out why and where is which wire and what's wrong. Okay. I mean, this is extreme. I think somebody just basically plugged in all the loose wires they could find into any holes. So this isn't a real circuit. And then we have Exhibit 2, which may be a little overkill. This is extremely neat, and if I had to debug it, I would much prefer this one. but you don't really want to make your wires as short as possible because you're probably going to have to change a few. So this is maybe not, these are two extremes. Okay, however, you do want to be neat and careful. You don't want your wires to be longer than they need to be. Okay. Insulation. So it used to be that we would have spools of wires, and students would cut their own wire and then have to strip the ends because, of course, you want the metal going into the holes to make contact. You don't want to strip all of the insulation off the wires because it, of course, serves a purpose. You don't want wires that are not supposed to be making contact to make contact, and that's what the insulation prevents, right? Okay. So you don't want to really strip too much more than the tip of the wire, a quarter inch. Now your wires will come in a little box and they're already pre-stripped. So I could have skipped the speech, but maybe in a future lab you will be stripping your own wires. Okay. All right, juice. All right, so nothing will happen unless you connect power and ground to your breadboard. And how do we do that? Well, each breadboard, each kit will come with an AC adapter. It's yours to keep. It's part of your kit. And so this will provide 5 volts, and I'm sure you have an outlet somewhere at home. And on the other end of this outlet, okay, you have the plug, which provides you 5 volts, and you can figure out which is ground and which is power by using a multimeter, or you can look at the back of the AC power supply, which will tell you. Your kit will come with this very useful little plug, and so you plug in your AC adapter here, and then one of these pins is power, one of these pins is ground, and the other pin just provides stability. Okay, again, you can figure out which is which using the multimeter. And okay, so you are going to want to supply power and ground to your breadboard. In CSE 100, you must run the power, the positive +5, through the fuse. So this is a 1 amp fuse. You will have 2 of them in your kit. Okay, and we don't want to ever come and find your breadboard without that fuse, or the fuse not being used properly, connected properly. But the idea is the power comes from the AC adapter, it goes through the fuse, and then goes everywhere else on your breadboard. In this particular case, you'll see that we've plugged in the fuse, or it used to be plugged in anyway. One of the problems is taking your breadboard somewhere else. Come on. Okay, there. Sometimes they tend to get destroyed. Like I noticed this wire came out, and that means I have a little piece in here, and then I need to go get my pliers and pull out that little piece. And if I can't, I'll just use another hole. All right, anyway, so all these little housekeeping details that you didn't have to deal with the FPGA, because the FPGA just magically wired everything up for you. Now you get to deal with next week, or this week. Okay. All right, this is broken. Okay, so I have power, and over here I have ground, and I'm kind of going to give away which pin is which, but oh, never mind. And if I plug it in my, whoops, something's wrong. I didn't do this right. Okay. I still didn't do it right. Why do I not have power now? Okay. I am plugged in. All right. Well, this wasn't the one I wanted to do. Anyway. So this is the one. I just plugged in. Okay. So I find it useful, this isn't required, to use one of the LEDs to indicate power. So this is a blue LED. You don't get a blue LED. You get just a standard red, green, and yellow. When I have power, when I'm plugged in properly and my fuse is still working, it will turn on. These are neat in that you can only see them from the top. If you try to look at the side, they don't look like they're on, right? Okay, my green LED is on, and my yellow LED isn't, and my red isn't. Maybe I can, this came out. Maybe I can switch that. Let's see. I think this is this the one? I can never remember which one is the clock and which one is D. That must have been the clock. Okay, that's D then. Okay, so you'll have these little switches that you can use to for the clock and the D input of your D flip-flop, and you can change those from power to ground using the switches, so you don't have to unplug the wire and plug it in all the time. And so this LED is just indicating power. This one is indicating the D input value. This one's indicating Q bar. This one's indicating Q outputs. Okay. All right. So juice should run through the fuse. And then what I suggest is you have power on one side and ground on the other, and that prevents accidents. You'll notice that the chips all have pins 1 and 14 as power and ground, and so you put them in the right way, they'll all pull power on the same side and ground on the opposite. Okay. Anyway, all right, so juice. Do not bypass the fuse. All right, so your ICs, you will plug across the continental divide so that their pins are all in holes that are not connected to each other. Yes? Doesn't have polarity. Either way. Okay. When you put when you get your parts, so you'll have a little box like this. It'll have parts in them, and there are my parts. You're going to need to apply a certain force to push them into those holes, right? You're simultaneously pushing in 14 different pins. Before you apply that force, make sure that your pins are aligned with the holes, because otherwise the amount of force you're using will actually bend the pins. And once you've bent the pin, it will break. And then you're going to throw that part in the trash. Okay, you will have, more parts than you need in your kit, but not that many more. And you can then go down to Bell's and buy a new part. Or you can beg somebody else in the lab to give you an extra part. Okay, so careful pushing them in. Make sure the pins are aligned before. Make sure you push down on both edges, because otherwise one will go in, the other side won't, and you'll bend the pin. Same thing if you need to pry them out. Get a little screwdriver or something, or a chip puller, and pry them out. Make sure that both ends come up together, because otherwise you'll bend the pin. Okay. So you're going to need to make a plan of how you're going to organize your parts on the breadboard. And you'll need to make a wiring diagram. Okay, so here is an example of a wiring diagram. It's different from a logic diagram. So for example, this is a logic diagram for half adder. We take two inputs. We need an XOR gate to generate the sum bit, and we need an AND gate to generate the carry, except we didn't have an AND gate. We had lots of NAND gates around, so we just used an AND gate, inverted it, and there's our carry. Okay, so how is this different from a wiring diagram? A wiring diagram shows where your parts are physically located, how they're physically located on the breadboard. And then it shows where each signal is going and how it's connected to the parts. Now, in order to know which pin is which, notice that pin 7 is ground, pin 14 is always +5. They do this on purpose so that if you plug it in backwards, you don't ruin the part. It won't work that way, but at least you won't kill it. Okay, so when you're debugging, trying to figure out why this darn D flip-flop isn't doing what it's doing, you're going to want to be able to trace the parts here. And this wiring diagram will be extremely useful. Okay, so you're going to want this. In order to figure out which pins on the part to use, of course, you need to know something about that part. So where does that information come from? Why, Google these days. You're going to look at the part number and Google it, and up will come the data sheet. We used to have books about this thick. They all turned yellow and went away now. They were on acid paper, so they're fluttered away. But of course, we have copies of them, and there'll be a very useful indication of what the particular function the elements of this part implements. So this, you'll recognize, is a NAND gate, and it says that if both inputs are high, the output's low, and if either input is low, the output is high. So X here stands for not unknown. It stands for either one. It doesn't matter. Okay, but most important, of course, is this indication of what each pin does. And these are the top views looking down. And this is perfect for breadboard because you're going to be looking down. If you were doing a PCB, or if you were doing what's called wire wrapping, nobody wire wraps anymore, right? You would need a bottom view, which is the reflection, okay? But you're not doing that. Okay, so this is a top view, and it tells you that, in fact, there are 4 NAND gates on here. And remember that picture up there? The inputs are A, B, and the output is Y. So that means that there's one NAND gate that has inputs pins 1 and 2, and its output is pin 3. So that's one NAND gate. And then there's another one, 2A, 2B, output 2Y, etc. So there's a total of 4 different NAND gates. And then, of course, you do need to connect power and ground, or those NAND gates are not going to do anything interesting. Okay? Any questions? So I know some of you have done all of this already. You've taken 171. You're probably rolling your eyes.
This is new for me.
But not everybody, right? Yes. For some of you, this is the first lab class, so I'm going over this in detail. More detail than you probably would like. All right. Okay, so how do you see the outputs? Well, one way to do that is using light emitting diodes. So as you can, as you saw when I plugged in one of my LEDs turned on, the blue LED turned on, indicating that I actually had power. My fuse was still good. So how do LEDs work? Okay. So this is a symbol for a diode, and an LED is a diode. It just happens to be a diode that emits light when you run enough current through it. A diode is a circuit element that allows current to flow in one direction only. Okay, from the anode to the cathode. Now, of course, you know, if you put 400 volts here, all bets are off. But within the reasonable range, current will flow. In fact, in order for current to flow, you have to have a sufficient voltage difference across the diode. Otherwise, very little gets through. Okay. The amount of difference that you need is called the forward voltage. And most multimeters will actually let you measure this value. And the other important thing to note is that these diodes, if you run too much current through them, they will be very bright for a very short time. And please, if you see a very bright LED, do not grab it with your hand because it might be very hot. Okay, pull the power out and let it cool down a bit, then you can pull it out. And hopefully you can fix it. It's still good, but maybe not. All right. So you do need to limit the amount of current that goes through your diode. There's a where's my picture? Ah, there it is. Okay, I'll get this picture. So these are the current voltage charts, curves for different colored LEDs. The blue requires much more current. But the red, the yellow, and the green a little bit more too. And you can see that they kind of turn on at this point. Okay, at between 10 and 20 milliamps, you can see the light, so to speak. So the diode, you may have enough forward voltage difference, but if you're not running enough current through it, you won't see anything. Okay, so you don't want to put a huge resistor there, but you do want to size it so that you have anywhere from 10 to maybe 30 milliamps. Try to stay under 20 because you want your LEDs to last, and you want to be green. Okay. I'm glossing over a lot of details. I'm sure that in your electronics class they talk about this in much more detail. Yes, I hope. Okay, the important thing here is you do want a current limit. Your kit's only going to come with 2 types of resistors, so you're not going to have a lot of choice as to what resistance to use, but it'll be fine. Okay. So I do want to mention that there are 2 different ways of connecting your LEDs. So let's say this is one of your parts. Maybe this is the output of a NAND gate, say. So when it's outputting logic 1, it's outputting a voltage and an amount of current for that voltage. And then that goes through the LED, the diode. And in order to run current through it, you're going to connect the other side to ground. And as I mentioned, you're going to put a resistor here because you don't want too much current to be drawn from the IC, and you don't want the LED to be too hot and burn out. So this is active high. Basically, when the output of the IC is high, the LED turns on. But we can do it the other way. This is active low. And when here, the idea is we're going to connect the LED so that its anode is actually on the plus connected to power supply. And we're going to run this through a resistor, again, because we want to limit the current. And so basically what happens is when the output here is low, when it's near ground, then you have current running through here. But when the output is high, you don't have a sufficient voltage difference across the diode to turn on the LED. Okay. This actually works better because ICs are a whole lot better at sinking current than driving current. Here you're making the IC drive it. Here you're just making the IC sink the current from the power source.
What is the IC again?
The IC is your chip. One of these chips. Say it's an output of one of these chips. And I know this looks strange because basically we've got, you're thinking of the diode as an input-output element. And there is a certain direction to it, but all it's doing is either allowing current through or not. And basically, if you think about what an IC is doing, remember when we built that inverter? Right? The output of that inverter was either sinking current, connecting it to ground through the pull down, or it was driving the output high with the pull up. So it's not really a direction of sending 1 or 0 out, it's making the output high or low. Okay, all right. So this is actually a more efficient way of connecting LEDs. Remember on the basis board, some of your LEDs are active high and some of them are active low. Which ones are active high? Yes.
The LED, the green LEDs?
Okay, but which ones are those?
LEDs 15 here.
Yeah, the ones next to the switches, the tiny, tiny ones. And which ones are active low? Yeah.
The anodes?
The anodes.
The 7 segment.
The 7 segment, the big ones, right? And now you understand why. Okay? They don't want to consume too much power turning those on. Okay. All right, so you can do that. And in fact, you can calculate, if you had a choice, you could calculate what resistor to select here to make the amount of current. In fact, if you want to look here, we can calculate, given that the output voltage will be some value. So again, we talked about outputs being a certain range depending on whether they are providing a logic 0 or logic 1. And using those two, you can pick a resistor so that you have current when the output is low and you don't when the output is high. Okay. Any questions on this? But absolutely you have to have a resistor. All right. Let's go back. All right, light emitting diodes. Okay, so we covered that. So many of you have used a scope before. Not a telescope, no, not a microscope, but not a oscilloscope, sorry. Okay. All right, those of you who haven't, you probably are going to want to spend maybe 15 minutes looking at this. So these are the scopes in the lab, the Keysight. They are digital scopes. We used to have analog scopes, and I love the analog scopes because they don't have an auto set. You have to set every dial yourself. The next best thing is we've disabled the auto set on the digital scopes. The purpose of this is for you to understand what a scope is and how to adjust it. I've labeled some of the buttons. This little web page covers the minimal amount that you need to use a scope. There are a ton of features and sophisticated things that you don't need to know about, but of course, you know, feel free to play with them. Just get your lab done first. Okay, but what a scope basically does is you connect a scope probe to a signal, coming out of your breadboard. And for part 1, that's going to be the ring oscillator. Just one place. And then it has, what a scope does is it shows you the difference in voltage between 2 points in your circuit. So you're going to want to connect the alligator clip, the other point, to ground, so that you're measuring your signal with respect to ground. And then it's going to show you on the screen over time the voltage difference. And it's going to keep sending sweeps. It's going to display the voltage difference over time, and you can control how much time is shown, and you can control the gain, or how much what the scale of the voltage is on the screen. One important thing is learning how to trigger, because if you have a signal that repeats and you keep watching it, you're just going to have a bunch of scribbles on the screen, and you're not going to be able to tell anything. So by triggering it, you see the same part of the signal over and over again, starting from a reference point, and then you get what's called a stable image, and you can actually understand what's going on. And to help you do that, I have one of these fascinating videos at the bottom that you can watch. It's all of 4 minutes, I think. All right. So spend some time. You can look at this before you even step in the lab. So that's a good thing to do, because you're going to need to display the output of your ring oscillator on the scope. So part 1, you build a ring oscillator, which is basically 9 inverters in a loop. And it just goes round and round and round and round, right? We are intentionally creating a combinational loop, and we're making it slow enough so that you can see it, and that's why there's 9. If you use 8 or you use 10, it's not going to oscillate, so make sure it's an odd number. 9 is the specific number of inverters. You'll need 2 parts for this, because each part will only have 6 inverters. Okay, and so then you'll display it on the scope, and you'll call over the TA and say, oh, look, I did it. And they'll give you your checkoff for this part. For part 2, you're going to be building that D flip-flop we've been using. And if you, from last time, you have on the lecture notes, you have a slide that has the design with 6 NOR gates. One of them is 3 input. If your part kit has NAND gates, there is an equivalent design which will take you about 30 seconds to find with Google. Okay. The inputs to your D flip-flop are the D data input and the clock. And as I mentioned, these can come from, these come from the switches, or you can use wires. And I used a yellow LED for the data input. So right now, D is high. I don't know which way clock is, but I have output. Green LED is the output Q, and the red LED is the output Q bar. Okay, and so right now, my flip-flop is holding a 1, and if I flip D, that wasn't D. Okay, if I flip D back and forth, that doesn't change my flip-flop. Okay, now I made D 0, and now I'm going to change the clock, and hopefully my flip-flop will then load a 0. Oh, amazing. It's always dangerous to do this. Okay, so now it has a 0. And now I'm going to change D again, and it stays. Okay, I'm going to even try that with the clock in the other position. Okay, it stays. Okay, now I'm going to make it change again. So I'm going to flip the clock, and it went. Okay, I'm going to leave it there, and I'm going to try D again. Okay, I'll make a clock low, and I'll make D. So basically, with either the clock low or high, you ought to be able to switch D, and the flip-flop doesn't switch. Only when D input is opposite of your content, opposite of Q, and then you flip the clock, then it should switch. Now, these are noisy connections, so when you make the clock go from high to low or low to high, you may get both edges, and it may load, and that's okay, don't worry about it. But when the clock is not moving, the Q and the Q bar should not change. Okay, all right, so those are the two parts. If you come to the lab and you have your wiring diagram all worked out and stuff, and you've read about the oscilloscope, you can be done in the first section easily. Okay, let me just take this away. Any questions on that? Yes?
So it'll be two separate demos?
Yes.
One for the other.
Two demos, you'll get two codes. Okay, and then there's a write-up, and this write-up is, of course, not nearly as involved because there's no Vivatos, there's no schematics or Vivato code to produce, no simulation screenshots. You want to take a picture of your scope before you shut it down. That might be a good idea, but not necessary. Okay, so that's Lab 7. Any questions? All right, there's one more thing we need to talk about in a little bit more in detail, and that's these data sheets. So, as I mentioned, you have different parts, and different parts, oh, yes?
Okay. Can we get now?
No. Yes?
Data sheets for the actual switches themselves?
Okay, the switch has 3 poles, and basically, depending on which way the switch is, the center pole is connected to the right or the left. And then you can flip it around, and it's the same thing. Okay? It's an interesting, in fall 22, we started using switches for the first time, and the people in the first lab section started blowing their fuses. And then we realized it was when they were flipping the switch. And we looked at the switch, and while it was being moved, it was momentarily making contact between the left and the right poles. And of course, left and right was power and ground. So it was blowing the fuse every time, often when you switched it. And so those switches got sent back. We now have new switches that don't do that. Okay. So the switches are really simple. They just have 3 pins, and the center is the common. Okay. All right. Did you have a question? No, he asked a question. Okay. All right. You probably can't read this, can you? Let me make it bigger. So this is a data sheet. We already looked at it to figure out the pinout of the part. But there's as you can see, there's quite a bit of other information here. So this is a part number, and there are different variation packages. So this part comes in 2 different packages, but pretty much everything else is the same. And it's a 74HC, very important, because that means it's CMOS. Okay, and let's see. So one of the properties of CMOS is that the outputs tend to go all the way to ground and power almost. So let's see that. So here's our output. So when we are outputting a 1 under we are all the way going to at least 4.4 volts. Now this is with a 4.5 volt power supply. And when we want to send out a 0, we're down at 0.1. So it's kind of like the full range here. If we look at the amount of current, it's very low, 20 microamps. Okay, so one thing about the current, if you remember, is that it has a direction. So if you have 2 points and you measure direction from point A to point B, if current is flowing from A to B, that's positive. But but in the same situation, if you ask for the current from B to A, it's the negative of the other direction, right? So the sign indicates direction of the current. Okay, so that's the CMOS part. Very little current and full range of the outputs. So what is considered a 1 on the input? In order for something to be received as a 1 or understood to be a 1, it has to be 3.15 volts. In order for something to be understood as a 0, it has to be below 1.35. Okay, so that's a big gap there, right? Almost 2 volt gap in between, no signal land. Okay, so this is a CMOS part. As opposed to that, let's look at LS, low power Schottky. So here we have 3 different packages. This one only has 2 NAND gates. And how is this different? So you will most likely get this type of part. Okay, so this is made with bipolar transistors, which I'm not going to talk about. But basically they are current driven. So do you talk about TTL at all anymore? In 171, no? All right. It's probably for hobbyists more than anybody else at this point. Okay. All right. Let's look at where is the output voltage? Okay. The output voltage is only 3.4. Right? We had 4.4 for the CMOS part, and 0.2 has to be pretty low to be a 0 now. Sorry, 0.1, right? Max 0.4, okay. Something is considered a 0 if it's below 2. Sorry, if a high is above 2. Okay, so this is quite a bit different than the CMOS. And 0.8 for a low. So these are different. These parts don't speak well to each other. Okay, if you have 2 parts of different families, you may need to have a translator in there. But the other thing that matters here greatly is the amount of current. Look at this. In order to make an input low, you have to sink 1.6 milliamps, not micro, milliamps. Okay. And these are providing milliamps. Okay, so this is something we haven't talked about yet, and so let's do it now, is fan out. Okay, so we talked about 2 parts devices having to understand the same language, have the same voltage levels to speak to each other, but they also have to speak loud enough. And that's it, and the analogy here is the amount of current they can provide or they can sink. So if you have, let's say we have a device here, maybe it's an inverter inside and it's providing an output. And one thing that you've done certainly in your designs is you've connected one output to more than one input, right? That's perfectly fine. Right? But now we need to make sure, remember Kirchhoff's law, the amount of current coming out here is going to sum to the current going into all of these guys. And so we need to make sure that this part can provide or sink the amount of current. So over here we have to worry about the amount of current it can provide when the output is high and the amount of current it can sink when the output is low. So this is current going in, and this is current going out. Okay, well, that depends on how hungry these parts are. And let's see, so we have each of these has an amount of current it needs in order to receive a high, a 1, and an amount of current it needs in order to receive a low. Okay, and this one too. Now let's assume that all of these are the same, so that I don't have to have subscripts for all of them. One important aspect of a particular logic family is how many inputs can I connect to a particular output. This is called the fan out. And so to figure that out, we calculate two things. We take the amount of current that the part can supply when it's high, and we divide it by what each input requires. Okay, now current has a direction, and this is because it's current going into a chip is considered positive, current going out of the chip is considered negative, and that's why over here you see we're talking about the high output current. That's why it's negative, because this is current leaving the chip. All right, so I need to put a negative sign around here, otherwise I'm going to get a negative value. If you get a negative value, that's okay, just ignore it, negative sign. All right, so what is that number? That number is, I lost it now, minus 0.4. So I have minus 0.4. And how much does an input require? Requires 40 microamps. Don't forget the units. Okay, 40 microamps. Okay, so what is that? This is 400 microamps over 40 microamps. Okay. What? 10, yes. 10. That means I can connect 10 inputs to an output when it's high. Well, what about when it's low? Okay, so we need to do the same calculation for low. Okay, so now I'm going to take my output low, and then I'm going to have to put a minus sign there. Okay, so output low, we can think 16 milliamps. And input low requires minus 1.6 milliamps. So it's minus 1.6 milliamps. So I have 16 over 1.6, which is 10. Okay, do you think that's a coincidence? No. Okay, so it doesn't make sense for one of the two numbers to be bigger than the other, right? Because you want it to work in both cases. So whichever number would be less would limit you, right? So these parts are designed to be balanced so that you can connect a certain number of inputs to the outputs, regardless of whether the output is high or low. Okay, all right. So this is how you calculate fan out. You do these calculations, and you can look it up. Any questions on it? Yes?
So the value that you get for fan out is how many other devices you can hook up to it?
How much that net can fan out, right? And if the numbers are different, which would you take, the max or the min? The min, right? Because you want it to work in both cases, so the min is all it's going to work. Okay. I think I've run out of things to say unless you have questions. I guess we could do this for the CMOS requires very little current. Where is the inputs, in fact? I can't even find it anymore. No, I lost it. Okay. So these data sheets, I don't even have the whole thing here. Some of them are like 20 pages because they have a lot of information, mechanical information, like how far, how many, what's the exact distance between the pins and the size of the chip. And of course, this is all very important if you're making a PCB board and you like the chip to actually fit. Okay. Any other questions? Oh, here we go. It's nanoamps. Yes? Okay. You want to do that? Did you have a question, Claire?
I was going to say, could you walk us through drawing a circuit, not a circuit diagram, a wiring diagram? So, both have walk us through a procedure question.
It's not really, I mean, what you're going to want to do is put your chips, draw your chips, right? And then you're going to need to know how the gates are arranged. So one way to do this, I will do the noise margin. Okay, I got distracted. One way to do this is, say, okay, I'm going to have a part here on my breadboard. I'm going to have a part here, and I figured out that there was internally there is an OR gate here. Wait, I have to draw an OR gate that's connected like this. Okay, so now you have this in your drawing, and then you're going to say, okay, I'm going to go out here, and then this OR gate's going to go over here, and over here I have an inverter. So this is going to go here. Okay, so it's actually showing the connections from pin to pin and where your gates are. Okay, all right, so noise margin. All right, so you want to do the noise margin. Okay, so we need, so people try to memorize those formulas, and it's an alphabet soup. And unless you're really good at memorizing them, I suggest that you just draw yourself a picture because it works so much better. This is the output high, this is the output low, and on the input side, I need the input low and the input high, and then it's clear that what I want to do is I want to do V output high minus V input high, and V input low minus V output low. They're reversed, right? But if you draw yourself the picture that you want this one to map into here, and you want this one to map into there, you won't get confused as to which is which. All right, so output high. So let's take this part, 4.4. 4.4 minus, and what is an input? It was up here, I think. 3.15. So this is the noise margin on the high side. This is the noise margin on the low side. So input low is 1.35 and output low is, I went past it? 0.1. Okay, so this will be 1.25 and 1.25. Okay, so the noise margin then is the maximum minimum of these two, which turns out to be 1.25. So about 1.25 volt noise margin. Okay. Now, these numbers here depend on a lot of things, like how much current you're drawing and exactly how strong your power supply is and whether you are in Death Valley at August 1st or Denali on December 31st. Right? Okay. So they're not set. They vary. They're trying to give you kind of nominal typical figures that you can use, or expectations. Any other questions? Okay. We'll talk about the FPGA on Wednesday.